So this PowerPoint will introduce you to the interclass correlation, or the ICC. I will talk about what the ICC is and how to calculate it and how to interpret it. And then secondly, I will also talk about why a small ICC does not mean you can run a regression analysis and just ignore the clustering of the data. So what is the ICC? There are three definitions on this slide, and I will talk through each of them. One way of looking at the ICC is that's the proportion of total variance in an outcome that is between groups. That means how much of the variation is between the groups compared between individuals. Kraft and Delu define and talk about the ICC as the degree to which individuals share common experiences due to closeness in space and or time. So this is more conceptual in terms of application. So in our case, it would be the degree to which individuals share common experiences in the gym. And how much does that account for the total variance? If we want to calculate the ICC, and this is why I say here in math speak, then you calculate it as the ratio between the level 2 variance, or the cluster variance, and the total variance. And the total variance is the sum of the level 1 and the level 2 variance. So it can also be thought of as the level 2 variance divided by the sum of the level 1 and level 2 variance. We will revisit this later on when we have 3 or more level models. Things get a little bit more interesting then. But so far, what you need to remember is that it is the level 2 variance that's actually in the numerator, and that the total variance is in the denominator. So if we're looking at a proportion, this is always below 100%, and that will help us understand how the data are clustered and will help us understand our findings. So how do we calculate the ICC? The first thing is we need those variances, and we need to locate them in the HLM7 output or in any other software output that you might use. So in HLM7, that table is called the final estimation of variance components. And what you see in this slide is the output from the bootcamp data. That table is always located at the almost very end. There's only the deviation down there at the end. After that, so it's the last table of the HLM7 output for the models that you will be running. And here you see I've already highlighted in yellow the level 1 variance, and it says level 1 down there in the output, and then it says R, the same R that we use in the equation. And then I've highlighted in turquoise the U0, which we label as a U0J in the formula, and it's labeled here intercept. And then I've highlighted the variance component. One thing that makes this sometimes a little bit error prone is that people take the number that's right next to the U and the R, so they copy the standard deviation, and that's not correct. We need the variances, so you'll make sure that you're pulling the numbers from the variance component part of the table. So here is the formula again, and we just need to find the pieces and do a little bit of simple algebra actually. So the level 1 variance from the table I just shown you is 1.97, and the level 2 variance is 25.5. So first you calculate the total variance, which is adding up those two numbers and gets you 27.5. And then the ICC is the level 2 variance divided by the total variance. So the 25.5 divided by the 27.5, and you get 0.9281, which, if you convert this into percentages, is 92.81%, which means the ICC for the bootcamp data is 92.81%. I want to point out again that these are fake data. These were created with a very specific purpose in mind to show extreme conditions. So you will never, I want to say, most likely never see an ICC that is high up to that level. I don't think in my real data I've seen anything above 30%. So how do you interpret this? So in this case, with a 92.81%, we could say the vast majority of variance in BMI is at the gym level. That means the variation in BMI is only 7.17% due to individual variation beyond variation between gyms. So where do I get the 7.17? It's just 100 minus the 92.81. So any variation that is not on level 2 coming from level 1 would just be the reverse of that. So again, you won't see any ICCs that high, but this is the general interpretation that it's the variation at the cluster level. Whether that cluster is a gym, it is a school, it is a clinic, it is a hospital, it is a neighborhood, any of those, it really translates nicely. So now it's your turn. Take the formula, take the following table, and calculate the ICC for that table. This table is the output from the unconditional model where I modeled physical activity as outcome and instead of the BMI as the outcome. So if you want to replicate that, you can just go into the HLM software and choose PA as the outcome instead of BMI, and you should be able to replicate this. So take those numbers and calculate the ICC and interpret the results. And as last week, put them in a Word document so that we can talk about it in class. So I get this question a lot. And a lot of people will point this out and people stumble over this in books. So I want to address this head on. What if I only have a small ICC? People come and say, how big does my ICC have to be so that I have to worry about it? And I've early on encountered examples in books, Kraft and DeLu have one in there, that point out that it really depends on your data. There can be very small ICCs that can have large impact. But there's still many, many people out there. This is an example from somebody that had brought this to me by Lee in 2000, where they argued that only when the ICC is more than trivial, and they defined this as greater than 10% of the total variance in the outcome, would the analyst need to consider multi-level models. So as you can see, I strongly disagree, and I want to say that this is not a good idea. This is a bad idea, and I will outline in the following slides why this is not a good idea ever. So why not? Why can you just not ignore the clustering if your ICC is small? Remember when we talked about assumptions, the assumption of homogeneity of variance might not be met. And if the assumption of homogeneity of variance is not met, you cannot run a regression analysis. What does that mean? Homogeneity of variance. The level 1 errors need to be independent of each other, so not dependent upon the cluster. The level 1 errors need to be normal distributed. I found a really nice example that Roberts presented at AERA, the American Educational Research Association, in 2007, where he simulated some data that show unique properties similar to our bootcamp example, how things could actually go really wrong. So let's take a look at this diagram. This is in the paper by Roberts, and it shows the residual error plots for the unconditional model per cluster. And what you can see on the left-hand side is the cluster number, and then we have these cat and whisker plots that show the mean of the residuals and the variation and the variance in those. So what do you see? First, what comes to my mind is that there is much more variation in group 30 than there is in group 1. And the data have been intentionally simulated that way, but what you see is that for all of these groups, the mean is pretty close to 0. Some a little bit more off, like group 28's, probably around 4, and we have some that are a little bit in the negative. But overall, what you will get is a very small ICC because they're really hovering around 0. So the ICC is actually below 1% in this data set. But looking at that, we see that the variance is definitely not comparable. So what does that mean? So this means while the ICC is small, and I already mentioned it's far below 1% in this data set, the variances are quite different across groups. What does that mean? That means the error variance is dependent upon group membership. That means the errors are not independent because they're dependent. And that means the assumption of homogeneity of variance is violated. And that is one assumption of regression. And therefore, you cannot run a regression with a data set where your homogeneity of variance is violated. So this is an extreme example where you have a small ICC, but because the homogeneity of variance is violated, you cannot run regression. You actually have to go through a lot of work to get to this point, so why not run a multi-level model right away? So I want to talk about the scenario where the ICC is small and you have shown that you have homogeneity of variance. So why then not just run regression? Because the world's a little bit more complicated than that. So adding an individual level predictor might change everything. And how? How can that be? So you can still have scenarios, and those show up quite frequently, where the variances might be similar across groups, but it doesn't preclude that the relationship between the predictor and the outcome can still vary across groups. So in different groups, different individual characteristics have a different impact on the outcome. The example that I've adapted from Robert's paper is, let's look at the outcome of a person's high school GPA. There's a reasonable assumption that it's distributed equally across schools, and I would guess that you would find a small ICC and that across schools the variation is quite similar. We have, with all the grade inflation and things like this, that the best students in the schools have really high GPAs and the worst students, things like that. So what if we want to look at the impact and the relationship of the PSAT scores on a person's high school GPA? Then things might look differently, because we already know that if we would use the PSAT scores at the outcome, that there would be probably, most likely, pretty definitely, no homogeneity of variance. Different schools have different distributions in PSAT scores. And this is many times due to a ceiling effect, if we're looking at higher performing schools, there will be a lower variance. If we're talking about mid-performing schools, there will be a higher variance, and the means will actually be different as well when you think about that. So you will get in trouble again with running a regression. So what does this mean? This means that we need to use HLM when there might be a group-dependent relationship between any predictor and the outcome. And I would challenge you to find those that you can reasonably argue, and nobody can poke a hole in this argument, where that is not the case. So just in case that, while I've tried to be very, very clear that this has not completely clicked, my take-home message is always investigate multi-level models when the data are clustered. Okay? And I added this note, even when the data are not clustered due to data collection, there might still be dependencies, for example, due to place. You have to poke at your data. You have to understand where independence of observations might have been violated due to the reality of data collection. Last but not least, here are the references. I had a quote from Grafton Delu earlier. This is an older book, but there's actually newer editions of those. It's just not on my bookshelf. There's I also quoted Lee with this whole idea of, oh, maybe if it's less than 10%, and people use this and they have used it, and it's similar to my reaction to approaching significance, marginal significance. In my opinion, that is not the right thing to do. And then I have the Roberts paper here, and I put that on Canvas for your reference, and also to pull this up in case anybody challenges you on this. Thank you.